Okay, so in this example, we're going to take a linear programming problem, and you can see it's a linear programming problem by the fact it has, two variables and they're all, linear. The 25x plus 30x2 and 20x1 plus 30x2 less than equal to 690, 5x1 plus 4x2 less than equal to 120, and your non-negativity constraints for x1, x2 greater than equal to 0. What we're going to do here is we're going to solve this linear programming problem using the geometric technique, which is basically just solving it graphically. We have two variables, it's really easy to draw a graph, and that's what we're going to do. So the first thing I'm going to do in this situation is just change the variables, because most of us are familiar with xy planes, so why don't we just make those variables x and y, just it's that it cements the idea. You don't have to do it, I'm just doing it to make it a little bit easier on us. So we have the objective function, and that is just 25x plus 30y. We have constraint 1. Constraint 1 is 20x plus 30y less than equal to 690. I'm leaving some space because I'm going to do some working out there. Constraint 2, 5x plus 4y less than equal to 120. And then we have, a non-negativity. So constraint 3 is x is greater than equal to 0, and C4 is y greater than equal to 0. So first up, these two are going to pretty much tell us that, hey, we're going to be in the first quadrant. So when we start drawing our graph, we don't have to overly stress, about doing the entire thing. So we know we're going to be having something like that. That makes our life, a little bit easier overall. And obviously that is your 0, 0 point. And that is going to be our x direction, and that is going to be our y direction. Okay, so let's move on a bit with this. So what we're going to do now is we are going to investigate just making our constraint lines a little bit easier to plot. So for constraint 1, what we're going to do here is we first going to actually just divide through by 10, because we know we can do that because we have those zeros, recurring everywhere. So we have 2x plus 3y is less than equal to 69. Now there's a couple ways that we can go ahead plotting straight lines. I'm sure you're familiar with them. I'm going to do the super basic, find the x-intercept and find the y-intercept. So if you find the x-intercept, obviously you set y equal to 0 and you solve for it. So here we have, 2x, and I'm going to leave it like this, but technically doing a straight line, so it's just equals to, and then you're going to have, your x is going to be 69 divided by 2, and I believe that is 34.5. Okay, so we have the x-intercept, so we have 34.5 and 0. Then we can find our y-intercept, and I'm running out of space there, so let me just do it here. And that's just setting x equal to 0 and solving for y. So we're going to have, that 3y less than equal to 69. So y is going to be less than equal to, and in that case, if we work that out, that is 23. So we have our y-intercept of 0 and 23. So for that line, we already have our x and y intercepts. We haven't chosen our scale. And so you shouldn't just start drawing. You should first wait to find out where all your intercepts and stuff are. So if you draw it to scale, because you technically should be drawing to scale, it comes out very, very neatly, and it fits in whatever you join. So let's move on to, C2, constraint 2, and go and investigate the x and the y intercepts there. So again, the x-intercept is where we set y equal to 0. So we're going to have 5x less than equal to 120. So x is going to be less than equal to 120 divided by 5, and 120 divided by 5 is going to give us 24. I need to double check that. 120 divided by 5, yes, it is 24. Okay, so you're going to have your x-intercept is 24 and 0, and then you can work out your y-intercept. Your y-intercept is going to obviously be where your x is equal to 0, so that's going to be 4y less than equal to 120. So y is going to be 120 divided by 4. This one's way easier. That is just 30. So we're going to have 0 and 30. Okay. Now we have these two. We can, set our scale of our graph. I'm not going to be exceedingly accurate about this because I'm just doing this rough to explain to you, but obviously when you draw this, it should be incredibly, to scale. I'm just going to wing it here and be like, well, this is approximately 24, and this is, approximately 34.5, and then I'm going to go, obviously, just to try and get, a very similar kind of approximation, that's like 23. And then we have the 30. The 30 should be, somewhere around there-ish. Okay, so now when we draw the line, obviously you're going to connect that 34.5 to the 23. And you're just going to draw it in there. And with this one, you will connect your 24 and your 30. Okay. So always when you're doing this graphically, you will plot your constraints as straight lines first of all. You will also then need to investigate where are those constraints being met. So that's the next step in this process. But the first one, what I want to do, I just want to label the constraints so that when we look at the graph, you can see what's going on. So constraint 1, again, it was connected to the one that's 34 and 23. So let's just put that as constraint 1 there so we can see, pretty clearly which one it is. And constraint 2. You can even, color them in kind of a situation. So you can have a situation where you just highlight it so you can actually see what is going on. And this is just going to help you, particularly like when you're looking at the corner points, because when you're looking for the corner points, you're going to need to know which constraints make up those corner points, particularly because if you solve it graphically, you're not going to have the most accurate corner points by just reading it off your graph. And the best way to do that is for simultaneous equations. So just color them in there. The next step here is to actually determine where the feasible region is. And to do that, obviously, you need to know if it's above or below the line. So there's two methods to go about this. There's the one method where you choose a point on one side of the line and you put it into your constraint and see if it's being met. So let's just do that for constraint 1 so you can see the idea of how it works. So here we have constraint 1 and we choose a point below the line or above the line. Below the line, the easiest one here is 0, 0. Like seriously, makes your life easy and you can quickly check because you're going to have 0 there, 0, 0 there. Is 0 less than or equal to 690? Yes, that means everything, below the line is going to fit our constraints. The other method let's actually just talk about this. We could also choose the point above the line. The easiest point to choose above the line is to actually find, above this line here. So this intercepts at 30. And this is at 34. That's a cool point, to choose in this process. Because for definite it's chilling over there. Or you can just choose something like 100 and 100 or whatever. So there's options for when you choose a point, is any point above the line, any point below the line, you put it in. And if it meets the conditions, so like that 0, 0 had a situation where 0 was less than or equal to 690, you're like, okay, then anything in that below the line region is where the constraint's being met. If we had to put in 34.5 and 30, it's going to come up with a situation where it's going to contradict what we are doing there. So we're going to have a value that's larger on this side than that one, and then that means that this is not being met, and that it means that side is not meeting the constraints, which means below the line is meeting the constraints. So you have those options to you by selecting the points. There is a slightly better way to approach it, and that is to actually just consider your line. So let's just look at that and make y the subject of the formula. So if you make y the subject of the formula, let's choose actually this one because it has a little less values in it already. So we have that 3y is less than or equal to 69 minus the 2x, and then y is less than or equal to, you have that minus 2 divided by 3x plus 69 divided by 3 kind of a situation. You already know what 69 divided by 3 is. We already worked it out. But it's 23, by the way. But here you automatically know that all your y's below the line are going to meet that condition. So you can read it directly off your straight line representation of the graph. And by the representation of a straight line, I mean this one that you should be familiar with, where you have y equals to mx plus c. Okay, so we know that for constraint 1, everything below the line is feasible for that constraint. Now, there are two ways that we can go about showing our feasible regions. We can either color in everywhere where our constraints are being met, and that means we would, color in this region over here for that constraint, or we can scratch out everywhere where it is not being met. I'm a huge fan of the scratching out because I like my feasible region to be clear for me to see, and I feel like when you color it in, it gets a little bit hectic the more constraints you have to actually make sure that all your constraints are being met in that area. Whereas if you scratch out what isn't being met, you end up with, a nice little white area where the feasible region is, or an area that does not have any scratchings, which makes it a lot easier for you to see. So I'm going to follow the approach of I scratch out everything where the constraints are not being met. So in my case, I actually color in, everything here, and it's just like scratching it out kind of a situation. Okay. Then we have to look at the next constraint. So you're going to do this for all your constraints that are in this mathematical, problem. So now you do it for constraint 2, and if you do it for constraint 2, again, you can use that 0, 0 in this case because it does feature over there. If you put 0, 0 here, that's 0, which is less than or equal to 120. So you know everything below that line has its constraint being met. You can also make y the subject of the formula, and again, when I'm talking about that, I'm just talking where I did it here. And if you do that, you have that 4y less than or equal to minus 5x plus 120, y is less than or equal to minus 5 upon 4x plus, and in that case, obviously it's the 30 situation. And now you can see from here directly, everything below the line has the constraint being met. One thing to note by that, and one of the reasons why I bring these up, is technically you could have done this from the beginning and drawn your straight lines from this. So there was, that option where you could just draw your straight lines from this. Another reason why I like using this format is because it will connect to your range of optimality. So when you're investigating your range of optimalities, you then already have your gradients for those constraints, to actually work out the ranges of the, coefficients of x and the coefficients of x2 in this case. So there is different ways. Use whatever way, is comfortable for you, as long as, you're doing the correct thing. So here we have everything below this line has its conditions being met. So the constraint is being met below that line. So utilizing my approach of I scratch out everything that doesn't work, it's all of this doesn't work. Okay, so we have that kind of situation occurring. We're not done yet because you have to do it for all your constraints. These ones are just really easy, the non-negativity constraints. So if you're looking at the non-negativity constraints, you know that everything on this side is not being met, and everything underneath here is not being met. So now we have, that feasible region occurring from here to there, to there, to there, and to there. So this is your feasible region. And you can see it's nice and clear. You can see where the corner points are and everything like that. So you have, your one corner point over there, another one over there, another one over there, and another one over there. Remember, your corner points are actually referred to as extreme points. And this feasible region, whenever you set up your linear programming problems, the feasible region is a convex set. And that basically means that, a non-convex set would be something like that, where if you draw a straight line from somewhere over there to somewhere over there, it crosses and it's outside of that set. So it's convex, and in this case, our feasible region is bounded. It doesn't have to be bounded to, have the optimal solution be occurring, but if it is bounded, it is definitely an optimal solution. Remember, with the corner point theorem, the optimal solution will occur at a corner point if an optimal solution exists. So in this case, one of these corner points is going to give us the optimal solution for our problem. So that's our next step. We actually have to find all these points for solving to see which one of those points are the optimal. Now, I know there is a way where you can actually just take your objective function, and what you do is your objective function will be tangent to the corner points, which will either be the minimization or the maximization, but we are following the approach where we actually substitute in your A, B, C, and D values, your corner point values, into the objective function to solve which one of them are going to maximize, which one of them are going to minimize. In this case, which one is going to maximize. So we know what A is, we know what B is, we know what D is pretty clearly. That's 0 and 0. This one is 0 and 23. And this is 24 and 0. The one we aren't super clear about is C. And again, don't read it off the graph. Your graph can be really wrong. There will be introduce extra errors to it. So you'll actually just take your two constraints that are making this corner point and solve them simultaneously to get those values, because that's going to give you a slightly more accurate answer than just reading it off the graph. So let's go ahead and solve those equations simultaneous. Okay, so we have your 2x plus your 3y less than equal to 69, and we have our 5x plus our 4y less than equal to 120. We can just, see that as equals 2 and see that as equals 2, because technically we are looking at the line itself. Now we can solve simultaneous equations. There's a few ways you can go about it. If you had made y the subject of the formula originally, so that was less than equal to 3x plus 23, and that was y less than equal to minus 5 upon 4x plus 30, you could have said that minus 2 upon 3x plus 23 equals minus 5 upon 4x plus 30, and then you could solve for x. Okay, so you put x on the one side, everything else on the other side, and solve for x. There is another way where you can use these directly, and let's just do that. So we have 2x plus 3y is equal to 69, and we have 5x plus 4y is equal to 120. And now when you do the simultaneous equations, we're going to follow the approach where, you have you work out via that. So you're going to multiply the first one by 5 and the second one by 2, so that we end up being able to cancel out our x. So if we do that, we're going to have 10x plus, and 3 times our 5 is 15y, and then we're going to have our 69 times by 5, and that's going to give us 345. Then we have our 10x plus 8y is equal to 120 times by 2, that's going to give us 240. And now we can just, subtract one from the other. So we end up with that 0x. 15 minus 8, gives us our 7y. And then we have the 345 minus the 240 gives us the 105. So now we have 7y is equal to 105. So y is equal to 105 divided by 7, and that's going to give us 15. Okay, so now that we have 15, we can now just substitute it into either the first one or the second one. It's not a big deal which one we substitute it into. I'm going to substitute it into 1. So we have 2x plus 3 times by 15 is equal to 69. So we're going to have 2x is equal to 69 minus 3 times by 15. You could have said 3 times by 15 first. I'm just, going with putting everything before I do the calculations. So 3 times by 15 gives us 45. So we have 69 minus 45. So what is 69 minus 45? Well, that is 24. So we have 2x is equal to 24. So we have x is equal to 12 because we divide through by 2. So we have that corner point is 12 and 15. Okay, so we can put it on our solution, our graphical solution, that corner point is 12 and 15. And now what we're going to do is we're going to substitute in all these points into our objective function. So let's have a new fresh piece of paper. So we have our objective function. It is max 25x plus 30y. Okay, and I'm going to refer to this as z. So z is a function of x and y. So we're going to put through for all our corner points. So we're going to put through for A, for B, for C, and for D. And if we do that, we're going to have Z and 0 and 23 is equal to 25, 0 plus 30, 23. We're also going to have Z for 12 and 15. This was B, by the way. This is C. I'm not doing this in order. I apologize for that. So we have 25, and 12 plus 30 and 15. And let's do for D. We have 24 and 0, and that is 25 times 24 plus 30 times 0. And A is 0 and 0. Technically A in this case, it's clearly not going to be the maximization answer, but let's just do it anyway. 0 and 30 and 0. So that's going to give us 0. And let's go ahead and solve for all those points. So for 24 and 0, 25 times 24 gives us 690. So we have 690 there. Then we look at, let's do, that gives us 600. Sorry, my bad. Really bad math on my side. 25 times 24 gives us 600. Then we have, 30 times 23, that gives us 690. And then we do the more difficult one of 25 times by 12 plus 30 times by 15, and that is going to give us 750. Okay, so we have all our values, and again, we are trying to maximize it, so we look for which one is biggest. So in this case, that's the biggest one. So we have that extreme point C, or the corner point C is optimal, and that is, you have your Z 1215 is equal to 750, which means that the carpenter should make 12 bookcases, I think. Let's go back and check. Oops. Well, okay, we haven't discussed that. So the person will, require 12 of X1 and 30 of X2. And that's it. That's how you'll solve it graphically, or the geometric solution. So step 1, you are going to plot your straight lines, so that we plotted our straight lines. Step 2, we investigate where are the constraints being met to create our feasible region. We created our feasible region. It will either be bounded or unbounded, but it will be, a convex set. And then we know that where we have our feasible region, if an optimal solution exists, it will exist at the corner point. So then we investigate what our corner points are. So we find our corner points. For the ones that are like that, we don't just read it off the graph. We solve the simultaneous equations to get that corner point. And then we're going to substitute in those corner points into the objective function equation. And when we do that, we then look for, it was maximize, so it was 750. If we spoke about minimize, we'd look for the lowest value. And then we, tell whoever is looking at the work, what is the optimal one? What does that actually mean? Sometimes it will be connected to a word problem, so we can also then convert back to the word problem, which will tell us what X1 represents and X2 represents. And that's it.